I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
We're reaching the limits of what electrons can do. For over half a century, faster chips and denser circuits have driven our digital world. But today, every new transistor adds heat, every clock cycle burns more energy, and progress is slowing. Data centers now consume nearly 1% of the world's electricity. The question facing researchers is simple, but urgent. What comes after silicon? The answer, many believe, lies in light itself. Welcome to the world of optical computing, a revolution where photons, not electrons, do the heavy lifting. Unlike traditional computers that rely on streams of charged particles moving through metal wires, optical computers use photons, particles of light, to process, transmit, and even store information. And photons, unlike electrons, don't collide or heat up as they move. They travel at the speed of light, carrying vast amounts of data through hair-thin waveguides without resistance. Think about it. Light already carries your internet across oceans through fiber optic cables. Optical computing takes that same principle and brings it inside the processor, using beams of light to perform logic operations, calculations, and memory functions. The potential gains are staggering. Optical signals can transmit information thousands of times faster than electrical ones, while consuming only a fraction of the energy. Today's supercomputers often waste up to 30% of their power just converting signals from light to electricity and back again, a process called OEO conversion. In an all-optical system, that loss disappears entirely. Imagine data centers cutting their power bills by 70% while processing global-scale AI models at light speed. But light's power isn't just in speed, it's in parallelism. Photons can occupy many colors or wavelengths and travel side by side without interference. That means an optical processor can perform multiple operations simultaneously, something that's extremely difficult for electronics. This natural parallelism makes photonic computing ideal for AI training, weather simulation, and image recognition, problems that demand massive simultaneous computation. You've already seen glimpses of this technology in action. Synthetic aperture radar uses photonics for ultra-high resolution imaging from orbit. Optical correlators power facial recognition and missile tracking. In hospitals, optical coherence tomography uses harmless light waves to see inside the eye. And autonomous cars rely on LiDAR, pulsed lasers that map the world in 3D to navigate our cities. But if photons are so powerful, why aren't all our computers running on light? The truth is, building an optical computer is one of the hardest engineering challenges in modern science. An electronic transistor is a tiny switch that can amplify or stop current with incredible precision. To do the same with light, we need materials that allow light to control light, a property called nonlinearity. Researchers use crystals like lithium niobate or gallium arsenide, where the refractive index changes depending on light intensity. This interaction lets one beam of light act as a switch for another, forming the foundation of optical logic. Yet these nonlinear effects are weak and require high power to operate. Optical transistors struggle with tasks electronics handle easily, like restoring weak signals, isolating inputs and outputs, or splitting data streams, what engineers call cascadability and fan-out. Without solving these, it's impossible to chain many photonic logic gates into complex circuits. And then comes the issue of scale. Manufacturing nanophotonic components requires exotic materials and atomic-level precision, far more complex than printing silicon chips. That's why even though some silicon photonic platforms now exist for data communication, fully photonic processors remain confined to research labs. Still, progress is accelerating. Around the world, laboratories are racing to harness light for computation. In the United States, DARPA and companies like Lightmatter, IR Labs, and Lightelligence are leading the charge, building photonic AI accelerators that bring light into data centers. MIT recently demonstrated a programmable nanophotonic processor, a chip that manipulates light waves to perform general-purpose computation. Across Europe, institutes such as IMEC and CEA-LEDA are developing photonic integrated circuits, or PICs, that can be produced with existing semiconductor tools. Their goal is to make light-based computing as scalable as microelectronics. In China, researchers at the Shanghai Institute built a 64-core optical processor for AI acceleration, and Huawei's optics networks already push terabits of data per second through photonic links. Japan's Riken and the University of Tokyo are creating optical signal processors and exploring topological photonics, circuits where light flows around defects without scattering. And in California, an astonishing breakthrough has emerged. Dr. Elizra Morandi's team at Caltech created an optical cellular automaton, a computer that calculates using pulses of light instead of electronic bits. Each pulse represents a cell, and they interact through interference patterns, performing computations literally at the speed of light. This system can run tasks like image recognition or random number generation thousands of times faster than digital electronics, with a fraction of the energy use. It's not science fiction. It's science catching up with nature. Light's ability to propagate, interfere, and self-organize makes it the perfect medium for parallel computation. And when paired with new materials like graphene and transition metal dicogeconides, which bend light in nonlinear ways, the dream of compact, low-power optical processors comes into focus. Some experts believe we'll first see hybrid systems that combine photonic interconnects with electronic logic, co-packaged chips where light handles communication and silicon manages control. These hybrid designs could eliminate most optical-electrical conversions, making data centers faster, cooler, and greener. Meanwhile, startups like PsiQuantum and Xanadu are pushing quantum photonics, using individual photons as qubits for quantum computers. These systems harness light's quantum properties of superposition and entanglement, pointing toward machines that not only compute with light, but think with it. The story of optical computing isn't just about faster chips. It's about redefining what computing means. By freeing ourselves from the limitations of electrons, we move into a world where data flows at the speed of light, energy costs plummet, and the boundaries between communication, computation, and intelligence blur. From AI and climate modeling to defense, finance, and healthcare, the power of light could reshape every field that relies on information. So while the road to fully optical computing is long, the direction is clear. Light isn't just the messenger of data anymore. It's becoming the medium of thought itself. Thanks for watching. Subscribe, follow, or visit IDSTH.com for more cutting-edge defense and tech insights. See you in the next one.